By the end of this lesson, you will have a clear mental map of foundations of machine learning. We will begin our journey on the left, discussing our motivation. We'll explore why traditional programming, which relies on explicit logic, often struggles with complex tasks like recognizing speech. Instead, we will see how machine learning flips this paradigm to learn from data. Next, we move to the center to focus on formalizing learning. Here we will break down the training workflow, defining key terms like parameters and understanding how data flows through a system to create an output. Finally, on the right side, we will dive deep into the 4 essential components that make up almost every machine learning system. First, we look at data and how we turn real-world information into numerical representations. Second, we examine the model, seeing how these network structures transform that data. Third, we study the objective function, which gives us a way to measure performance. And fourth, the optimization algorithm, which is the engine that actually minimizes error over time. Anchor takeaway, machine learning is not magic. It is a structured process composed of 4 specific components: data, model, objective function, and optimization working together in a loop. Now that we have our roadmap, let's zoom in on our first stop, the motivation behind moving from traditional coding to learning systems.
Let's look at a coffee scenario to see how embedded machine learning already is in our daily lives. In this story, we have Alex here, who starts by saying a wake phrase, "Hey Siri." This wakes up the device right here. Once awake, Alex gives a more complex command, directions to Blue Bottle Coffee. Now, for the phone to actually do this, it can't just understand English like a human. It triggers a chain of events. First, it must transcribe the raw sound into text. Then it has to recognize the intent, figuring out that Alex wants navigation, not a web search. Finally, it can launch maps. What looks like one action to us is actually multiple machine learning models working in sequence. Let's zoom in on just the very first step to understand the engineering difficulty. This is the wake word challenge. We need to build a system, specifically a wake word model, that can tell when someone is speaking to it. The output we want is very simple, a binary yes or no. Did they say the word or not? But the input is where things get messy. The microphone doesn't hear words. It captures an input audio stream. Physically, this is a stream of air pressure values, often sampled at 44,000 samples every single second. To the computer, the "Hey Siri" command looks just like this jagged waveform of numbers. Now imagine trying to write a traditional program to solve this. Could you write a set of manual rules, like if the wave goes up by 0.5 then down by 0.3, to identify the word Siri across all accents and noise levels? It is extremely difficult. The data is simply too complex and high volume for human-written rules. This limitation, our inability to manually program rules for complex sensory data, is exactly why machine learning is needed. Here is the key takeaway. Machine learning allows us to solve problems where the rules are too complex to be explicitly programmed by humans by learning patterns from data instead. So instead of writing rules, we collect examples, which leads us to the concept of a data set.
The machine learning approach completely changes how we solve this problem. Instead of struggling to write explicit instructions for the computer, which has no explicit rules for hearing, we rely on the fact that, for us, recognizing speech is an easy task. We leverage this human capability to build what we call a dataset. This is simply a large collection of audio examples, like recordings of people speaking. Crucially, each recording is paired with labels, a yes if the wake word is present, and a no if it isn't. Now, instead of writing a fixed program, we create a flexible program. Think of this as a generic box equipped with many tunable knobs. In machine learning terms, we call these knobs parameters. By turning these knobs, we change how the program behaves. When we set the knobs to a specific position, that specific configuration is called a model. And because there are infinite ways to set these knobs, we have access to an entire family of models. So, how do we find the right setting? That is the job of the learning algorithm. This is a metaprogram, code that writes code. It uses the dataset to guide its search through the family of models. To make this work, we must define the wake word problem precisely. We feed an input audio snippet into the model, and it produces a classification output of either yes or no. The algorithm's ultimate job is to find parameters that make the model's output match the labels closely. In short, instead of programming the solution directly, we program a learner to find the solution for us by adjusting parameters to match data. But once we have this flexible machinery, does it work for just one task? Or can this same family of models learn to recognize completely different things?
So, what exactly defines a model? A well-chosen model family provides the structural skeleton. It gives us the general shape of the solution, but it's not rigid. Inside this structure, we have adjustable settings, which we call parameters or knobs. Think of this flexibility like tuning a radio. The radio is the structure, but you turn the knobs to find different stations. For example, we can take this same structure and tune the knobs to recognize the word Alexa. But later we could take that exact same structural family, simply change the settings of the parameters, and teach it to recognize the word apricot. Because these tasks are intuitively similar, they are both audio recognition. They can share the same model family. However, if we look over here, we see translation from English to Chinese or tasks like image captioning. These are fundamentally different problems involving text and visuals, not audio. Therefore, you cannot simply tweak the knobs of an audio model to fix them. They require entirely different families of models. Now, how do we find the right settings for those knobs? That is the process of learning. When we start, we begin with a randomly initialized state. At this point, the knobs are set to random positions, so the performance is poor. It won't recognize anything effectively. We then enter this design phase to create our model instance. The learning happens in an iterative loop. First, we grab a batch of new data. In our case, this consists of audio snippets with yes or no labels. We feed this data into the model and then perform the most critical step. We move up here to update the model. This is where we mathematically tweak the knobs to make the model slightly better at predicting this specific batch of data. Once updated, we drop down to check if the performance is good enough. Usually at the start, it isn't, so we follow this path back to the beginning of the loop, grab more data, update the parameters again, and check again. We repeat this cycle thousands or millions of times until finally the check passes and we output a trained model. At this stage, the parameters are correctly set and we have good performance. The key takeaway is that training is simply the automated process of iteratively adjusting a model's parameters to minimize error on a dataset. This concept of learning from data is what allows us to, quote, program complex behaviors without writing explicit rules.
In essence, instead of manually coding complex rules, which is incredibly difficult for tasks like recognition, we use a powerful approach called programming with data. The core idea is that we don't tell the computer how to recognize something step by step, we show it examples. We start with a labeled dataset. For instance, we might have folders full of images labeled cat and dog. We feed this data into a learning algorithm, represented here by this brain icon. This algorithm processes the data, looks for patterns, and eventually builds a model. This model is the actual software artifact that we can use to make predictions. Let's make this concrete with a specific example. Cat detector. Suppose we want to detect if a cat is in a picture. We feed our trained model various input images. The model analyzes the pixels and outputs a score. If it sees a clear cat image, it outputs a large positive number, indicating high confidence it's a cat. If it sees a dog, it outputs a large negative number, effectively saying definitely not a cat. And interestingly, for blurry or ambiguous images where it's unsure, it outputs a value near 0. This numerical output allows us to interpret the model's confidence. Now, let's look at the right side to see how this applies to supervised learning, which is the formal name for this process. Let's use the wake word example, like detecting, "Hey, Alexa." Here, our labeled dataset consists of audio clips, some containing the wake word, checked, and some without, crossed out. This dataset acts as the teacher. We pass these thousands of audio examples into the training phase, denoted by the stopwatch, because this process takes time to compute. The result of this training is once again a trained model. Once we have this model, we can give it a new input, a piece of audio the system has never heard before. It runs through the model logic right here and generates a predicted label, telling us whether the wake word was spoken or not. The key takeaway is that in supervised learning, we map inputs to outputs by training a model on a dataset where the correct answers are already provided. Next, we will break down the 4 universal components that exist in almost every machine learning problem.
Regardless of the specific problem we are trying to solve, machine learning systems almost always consist of 4 core components: Understanding how these pieces fit together is essential. First, we have the data, which contains the examples we learn from. This data is fed into the model, which transforms that data into a prediction. To know how well we are doing, we use an objective function to quantify performance. And finally, based on that score, we use an optimization algorithm to adjust the parameters and improve the system. Let's break down the foundation: data. Data is a collection of examples, which we need to convert into numerical representations called features. These are the inputs the model actually sees. Take a look at this image example. To a computer, this picture of a cat isn't fur and whiskers. It is 3 grids of numbers representing red, green, and blue intensities. If this image is 200 by 200 pixels, that results in 120,000 values. That massive list of numbers is our input vector. In supervised learning, we also need a target to predict, which we call the label. In this case, the label is the category cat. Now consider a medical example. Here, the features aren't pixels, but patient attributes like age, vitals, and medications. We use these to predict a binary outcome, such as survival within a 30-day window. The shape of this data matters. When every example has the exact same number of features, we call them fixed-length vectors. This is the standard dimensionality of the data. However, real-world data, like reviews or text, often comes as varying-length data because one review might be 3 words and another might be 3 paragraphs. Modern deep learning models are particularly good at handling this flexibility. Finally, we must consider quantity and quality. Generally, having more data allows us to train more powerful models. This is the big data advantage. Some models simply won't work without massive datasets. But quantity isn't everything. We must avoid the trap of garbage in. If your training data is flawed or contains historical biases, you will get garbage out. This leads to model failures, where the system automates injustices or fails on specific demographic groups. The takeaway is that while the model and algorithm get the glory, the data is what determines the ceiling of your performance. So with our data prepared, we are ready to feed it into the computational heart of the system.
Let's break down the core machinery of machine learning. It all starts with raw data over here. This data is fed into a computational system we call a model, which processes the information to produce a useful output, like a prediction. We focus specifically on statistical models, meaning the internal rules aren't manually hard-coded, but are estimated from the data itself. Now, consider the structure of these models. A simple model might consist of just one layer of transformation: input, process, output. But deep learning is different. In deep models, we don't just transform the data once. We pass it through a chain of many layers: transformation 1 to 2, and so on. This architecture of many successive transformations allows the model to learn complex and hierarchical patterns and gives the field its name. But how do we know if the model is actually learning? We need a formal measure of performance, known as an objective function. Since we usually want to reduce errors, we frame this as a loss function, where lower values are better. The specific formula depends on your task. If you are predicting a numerical value, you typically use squared error. Mathematically, this calculates the square of the difference between the prediction and the true value, and we try to minimize this number. On the other hand, for classification tasks like cat versus dog, we look at the error rate. This is simply the fraction of incorrect predictions over the total. However, this step function is difficult to optimize because it lacks smooth mathematical derivatives. So in practice, we often swap it for a surrogate objective that is smoother and easier for the computer to work with. Finally, let's talk about how we train these models without cheating. We take our source data and split it into 2 buckets. First, the training set, which the model uses to learn its parameters. Second, the test set, which we hide from the model to evaluate it later. If the model performs well on both, we achieve generalization. That's the goal. But if it aces the training data, yet fails the test data, as seen here, we have overfitting. Think of it like a student who memorizes the practice questions, but then looks completely confused when new questions appear on the final exam. The key takeaway is that true learning isn't just memorizing data, but finding a generalized model that minimizes loss on unseen examples. Next, we will discuss the specific algorithms we use to find those optimal parameters.
We start by establishing the prerequisites for training a deep learning system. First, we gather our data, which serves as the foundation. We feed this into a model, usually a neural network, that processes inputs to make predictions. The performance of this model is measured by an objective function, represented here as L of theta. Our ultimate goal is to minimize loss. As you can see in this graph, we want to slide down the curve to reach the minimum loss, the lowest point where errors are smallest. To achieve this, we need a robust method to guide us. The industry standard optimization algorithm for deep learning is called gradient descent. Think of it like navigating a landscape. Imagine you are on a mountain and need to find the way down to the bottom of the valley. It is a process of iterative improvement, taking one step after another to get closer to your destination. Let's break down the gradient descent as a core idea into specific steps. We begin with initial parameters, denoted as theta. These are often just random guesses to start with. Then we enter a learning loop. First, we check loss change. Mathematically, we calculate this gradient symbol, triangle L, which tells us the slope or steepness of the error at our current position. Using this information, we find the gradient or steepest path downhill. Once we know the direction, we perform the most critical step. We update parameters. We calculate the new parameter values using this formula. Theta new equals theta old minus alpha times the gradient. Notice this symbol alpha here. This represents the learning rate. The learning rate controls your step size. If it's too big, you might overshoot. If it's too small, you'll move too slowly. We don't just do this once. We repeat this many times, looping back to check the loss again with our new parameters. This creates a progressive adjustment. If you look at this graph on the right, you can see how the model's parameters move down step by step through the valley. Eventually, they settle at the bottom, moving towards minimum loss, which gives us the best possible model. Gradient descent is simply an iterative process of taking small steps in the direction that reduces error until the best possible model is found. Now that we understand how the model learns, let's look at the specific neural architecture we use to process this information.